Okay, so good morning, everyone. Hello, and welcome to our next seminar of the Research Division. Today we have the Thomas Hajnik to give a seminar to us, and I'm going to let David introduce you to him.
Good morning, thank you for coming. It is for me a great pleasure to introduce to this speaker, Thomas Hajnik. He finished his undergraduate studies in the University of Vienna in 2023, specialized in infrared spectroscopy of young stellar objects. Then he moved to Institute of Astronomy in Cambridge, where currently he's a second-year PhD student working in how stellar environment influence the formation of planetary systems. He's here for 3 weeks. Now we are in the middle of his visit, working in with staff. So he will still be here for another week, from Monday to Friday, but he will go to La Palma Tuesday to Thursday. So you want to reach him asking anything related with WIF or the talk he's gonna give. So be very welcome. It's in the first corridor, first floor. Unfortunately, we will not have coffee after the talk, but more importantly, tomorrow we are planning to go for Aguachinche. Tomorrow on Friday. So if you want to join us, so feel free. We are a small group, so we are very welcome. So leave the floor for him. Thank you so much.
Thank you very much, David. So firstly, I want to thank you all for giving me this opportunity to present today. I will be presenting the WIF Twilight Survey, which is a multi-object spectroscopic survey focusing on unraveling links, chemical links between host stars and their planetary, their planets, basically. So to give a quick outlook of what you can expect from today. So first, I will go very briefly in a very short summary, tell you a little bit about the most widely discussed planet formation models, and then I will go further into what chemical connections we have found between stars and planets so far. Then I would like to be able to convince you that it's very, very important for exoplanet studies to actually find an efficient observing mode to look at bright stars. I will explain in detail why I think this is important. And then actually I will be showing you the new observing mode that we have developed for WIF to actually enable these efficient observations. Last but not least, I will go into a little bit more detail about the WIF Twilight Survey, about the current state and the survey design. And also I will be giving you some glimpses into recently taken test data from WIF. So stay tuned, basically. Good. First, I want to start with how do planets and stars form? Well, stars, of course, form in star-forming regions. These are these wonderfully, exceptionally beautiful regions, like here, Rho Ophiuchi, taken with the JWST. And what we see if we zoom in into these regions is we often find these conical structures with outflows going out. And so what are these? Well, these are, of course, young stellar objects. And if we switch to another source, also taken with JWST, we can actually see a protostar in the making. It's a young stellar object of class 1, which is a very young stellar object. If we zoom in here even further, we can actually see that around the in front of the protoplanetary source, you can see this dark band. And this dark band is, of course, a disk, an accretion disk onto the star. And what also happens in this disk is, of course, protoplanets can form at some point. So here I cheated a little. This is, of course, a different source. But if we go to the submillimeter regime, we can actually look at these disks. And over the last years, we found a plethora of different morphologies in these disks. We find you can't really see it nicely, but kind of like spirally structures in the disk. You also find binary disks. But what many of those have in common is, of course, these dark bands. So in these dark bands and these gaps, we believe that planets are actually forming or have been formed, which means they basically just accrete material in their orbit and then lead to these gaps. So now a little bit about planet formation, as I said very briefly. So the predominant model of planetary formation that we discussed today is the pebble accretion scenario. So basically in these disks, planets can form as dust and ice particles coalesce together and form planetesimals. And if these planetesimals at some point reach a critical mass, around 10 Earth masses, a runaway accretion effect comes into place. And this runaway accretion basically leads to the protoplanet sweeping up huge amounts of hydrogen and helium from the disk, leading to essentially what we know as gas giants. If a planetesimal does not reach this critical mass, well, then we end up with smaller rocky-like planets, like we see, for example, as Earth or Mars or Venus, with much less thick atmospheres. Then, just for a matter of completeness, I also talk a little bit about the disk instability models. So this is a model where gas giants can actually form directly in the disk from gravitationally collapsing regions. But as to my knowledge, this has not been observationally confirmed yet. So I just mentioned here for completeness, as I said. So if we think about it, we know that stars and the planets definitely come from the same materials. So if we now look at the fraction of mass that ends up in planets from the disk, and if we do this in the solar system, what we actually found is that only 0.14% of the solar mass is actually ends up in planets. So it's actually tied in planets. So what this means is the rest needs to go somewhere, and the majority is actually accreted onto the star. And here, now it becomes a challenge if we want to actually find these imprints of planetary formation in stellar abundances, for example. So it's a big challenge to quantify these kinds of relations, and this is due to the fact that we have 2 orders of magnitude difference between the abundances in the planets and the abundances in the stars. And this, of course, prompts us to that we want actually very high precision abundance data sets. So we need abundance precision of roughly 0.04 dex, according to the Baimhart 2023 paper, to actually be able to measure any imprints of planetary formation in stellar abundances. So what this tells us is that all the trends we might see are definitely not very pronounced. So they're very subtle in nature. And this actually prompts us that we want large homogeneous data sets, homogeneous in a sense that they come from the same telescope, the abundances were derived with the exact same technique, in order to actually make these trends visible with a large sample size. So now a little motivation. Why would we even think that we can see these subtle trends? Well, in 2015, Theobald and et al. Actually simulated planet formation around different types of stars. And what they found is that the magnesium silicon and iron silicon ratios of the planets in their simulations remain very similar to those of the host star. You can see this here on the right, where we have the magnesium silicon planetary mass ratio versus the magnesium silicon abundance ratio for the stars. And you can see it's a very tight fit. And this fit is true actually for different planet types as well. And also, if we look at the solar system, we actually observe this. So if we look at the molar ratios of these elements in the sun, Earth and Mars, they are all within 10%. So what this prompts us to believe is that the composition of exoplanets, or planets in general, of course, is mainly influenced by the stellar abundances rather than by processing in the disk. And if you think about it, this kind of makes sense because magnesium, iron, and silicon are elements with a relatively high condensation temperature, which means they are solid over a large regime of temperatures, meaning that planets can actually form from these materials. So Theobald et al. Actually also looked at the CO ratio in their simulations, and what they find here's the same plot, CO planet ratio and CO star ratio, is that for a relatively small range of CO ratios, we find a large planetary CO ratios, we find a large range of stellar CO ratios. And what this means is, and this also makes sense, of course, because CO is mostly locked up in ices. So in this case, planetary formation becomes a matter of location in the disk. So depends on if you form further in, these elements will be, as they are volatiles, will be in its gas phase. If you form further out, they will be in its in solid phase, which means different scenarios, different accretion scenarios for the planets that can form. So basically what they find is the CO ratio varies too much to be able to find a link between the host star and their CO and the planetary CO ratio. Good. Now probably the most famous star-planet connection we have found so far, and probably also one of the most robust ones. It's the relation between the occurrence of a planet and the metallicity of the host star. So even in 2005, with a relatively small sample, Fisher et al. Actually found that high metallicity stars seem to have a higher probability for hosting giant planets. Later, 10 years later, this was generalized to other planet types, gas dwarfs and terrestrials. So in general, you can say, if you have a higher metallicity stars, the probability of this star hosting a planet is higher. This comes from, so the interpretation there is, if you have a disk with high metallicity, of course you have more material that can form planets, and also the disk lifetime actually is longer for high metallicity disks. So you have more, just more chance of forming more planets, of course. This is, as I said, one of the strongest trends we can see, and you can see this even in inhomogeneous data. So here on the right, I plotted the metallicity distribution of planet hosts in yellow and the metallicity distribution of non-hosting stars taken from the Hypatia catalog. The Hypatia catalog is a catalog of stellar abundances, which is a complete amalgamate. So they're from different surveys, a completely inhomogeneous data set, but still what you can see even by eye is that the non-planetary, the planetary hosts seem to be further right to higher metallicities. So this is for a data, and also of course we have a relatively high data, large sample size of 1,700, 1,800 host stars. Yes. All I could find. I just I took the complete Hypatia catalog, did not sample, made no mass cuts or anything. I just took it, planets, known planets, and plotted it. So there's no mass cuts in there. It's just all the stars with planets in this catalog. Of course, you're right. So just for the sake of this plot, I have not considered any of this. But in the catalog, they actually have flags, and the last time I checked, I think they actually have they filtered out most of the brown dwarfs they could find, I think. Yeah, they're not in there. Yes, exactly. Yeah, no worries. Okay, so next very interesting relation that was found in 2012 by Adebekian is the occurrence alpha abundance relation, where we find, they found in their data that there was a higher frequency for giant planetary hosts with increasing alpha element abundance. So alpha elements are, of course, elements coming from the alpha process in the star, so it's magnesium, silicon, sulfur, and so on. So what they actually found is, as I said, a higher frequency for giant planet hosts with increasing alpha abundance. And they also found something interesting, namely that lower mass hosts seem to have a higher alpha abundance. You can see this here plotted as two cumulative distribution functions. So the low mass planet hosts in blue and the giant hosts in red. And the black dotted line is the comparison sample without planets. So here you can see this shift from for especially pronounced with magnesium to higher magnesium abundances for low mass planet hosts compared to the giant hosts. Here sample size is 135, so kind of okay, but not the best. But it's if for later examples I will show you this is actually a very good sample size. So next would be connections people have found or claim to have found between planetary parameters and host star chemical abundances, or in this case, metallicity. So there seems to be a trend with eccentricity and higher metallicity. So high eccentricity planets seem to be preferentially found around metal-rich stars. So in a plot from Mills 2019, you can see this again, two distribution functions. High eccentricity systems here on the left, on the right, and low eccentricity systems here. And you can see even statistically, they actually find a significant difference. Okay, again, we need to talk a little bit about sample sizes. In total, they have 440 hosts, but if you look at this line, this is 1, 2, 3, 4, 5, 6, 7, maybe 10 high eccentricity planets. So of course, there's some bias, but these are the numbers, or these were the numbers in 2019 they had to work with. Also, what they found very interestingly is that often when they looked at their high metallicity, high eccentricity planetary systems, they only found one single giant planet. And they interpret this basically as a sign that this is not the only planet in the system. There might be more planets in the systems, but if you think of it about in terms of the occurrence metallicity relation, it's more likely that a high metallicity disk forms a giant planet. This giant planet then over time, like very likely Jupiter and Saturn did in our system, interacts with the other stars, raising their eccentricities, raising their mutual inclinations. And in terms of observations, for us, especially transit observations, this means with higher mutual inclinations, the probability of actually finding those planets goes down quite a bit, because towards our line of sight, it's not it's not really given that you can find the planet going in front of the star. So this, this would be one of the planetary parameters and stellar abundance connections. And the next one I show you is from a relatively recent paper from 2024 from Tautoviciene. And what they claim to have found is a relation between the planetary masses of the system with the stellar chemical composition. And if we look here on the x-axis, the planetary masses of individual planets per star is plotted against metallicity, carbon-oxygen over oxygen, and magnesium over silicon. And so what Tautoviciene et al. Claimed to have found is that for high mass planets, there seem to be a higher, on average, they have a higher metallicity stars. You can see this here per eye. And if you look at it just with your eyes, kind of, in numbers, it's 0.2 dex. I would say this is one of the more robust arguments in the paper. But if we go to the CO ratio, they also claim to have found a difference, and they see basically low mass planets have higher CO ratios than the stars. Of course, the low mass hosting stars have higher CO ratios than the high mass hosting stars. I put these question marks here because not without a reason, and due to the fact that here the sample size is roughly 25 hosts with roughly 100 comparison stars with no hosts. So of course, there's another relation they show where lower magnesium silicon ratios seem to be present for high mass planets. Well, yeah, as I said, sample size relatively small, but if those trends exist, this would be very interesting and very exciting, actually, because this would show us that we can find this. Again, next connection could be between lithium depletion of planetary hosts, so depletion effects in the star. So Ratham et al. In 2023 found actually that there's possible lithium depletion in exoplanet hosting stars. And you can see this here on the plot, where the purple line actually plots the median lithium abundance of stars without planets versus the differential lithium abundance of individual planetary hosts. Again, sample size 36, so please take this with a grain of salt. But on average, what they find is that the planetary hosts seem to be depleted in lithium around minus 0.23 dex. Another possible depletion connection is claimed by Yun et al. 2024, also relatively recently. And what Yun found is that giant planet hosts seem to be more depleted than rocky planet hosts. So first of all, how do you measure refraction depletion? Well, refraction depletion in this paper is measured by using the abundances of refractory elements, in this case, magnesium, aluminium, silicon, calcium, manganese, and nickel, and then plotting them versus their condensation temperature. And if you then measure the slope in these plots, and the slope goes to the negative, then you can say, okay, the more negative the slope is, the more depleted they are in refractory elements, and the more positive the slope is, the less depleted they are, basically. And so now they split their sample into exoplanet hosts that host giant planets and rocky hosts. You can see here the slope distribution on the x-axis, and the giant hosts in yellow and the rocky hosts in blue. And I underlined the median of the two, and basically what this tells us is that the median of the slopes for the giant hosts is lower than for the rocky hosts. What they also did, they then more closely looked only at terrestrial planets, and the terrestrial planets seem to be more depleted with the number of rocky planets the system hosts. So here you can see again the slope distribution of systems with less or equal to 2 rocky planets, and then you can see the ones in yellow for more than 2 rocky planets. And again, the median for the more than 2 rocky planets seem to be high, less than the median of the systems with less rocky planets. So again, all to be taken a little bit with a grain of salt. They at least used the apogee data set, so they have a relatively homogeneous data set. But what really goes into these calculations is you have to take into account kinematic effects. You have to take into account the galactic chemical evolution. So every step on the way brings it with new uncertainties, and with a sample size of roughly 170 planets, this might lead to significant biases. So if we now sum up all the connections I told you about today, and I definitely missed some and omitted some because the talk is going to be too long. But in this case, what we can actually find is that the only ones that are really robust and have been reproduced over the years in multiple studies is the occurrence with metallicity and occurrence with alpha over abundance relations. The others still lack definitive evidence. And this is due to the fact that if these effects are there, they are very subtle. If also you have to take into account the uncertainties introduced by how these values are derived, how the abundances are actually measured, etc. So if these trends are there, what we would like to do is we would like to have more data, as always in modern day astronomy, to actually somehow find these trends in larger data sets, so we can convince ourselves that this is actually something we're observing. Okay, so how could we do this? Well, here comes WEAVE. So many in the audience are probably very familiar with this instrument. So WEAVE is short for the Wilhelm Herschel Telescope Enhanced Area Velocity Explorer, and it's based at the Wilhelm Herschel Telescope in La Palma, and it is a multi-object spectrograph with a circular field of view of 2 degrees, which corresponds to roughly pi square degrees in area. So it comes with 2 observation modes. a low and a high resolution one. The low resolution one has a spectral resolution of 5,000 and the high has a spectral resolution of 20,000. Coverage is in the optical from 3,600 to 9,600 angstrom. And basically how it does observations is it places individual fibers onto a field plate. And this field plate is then placed into the light path of the telescope. And so we get one spectrum per fiber, which could be a star or a galaxy or a QSO or whatever you want to look at. In our case, it's of course stars. So a little bit more about the instrument. So you can see here the fiber positioning apparatus installed on the William Herschel telescope. And this is Gavin Dalton, and one of the PIs. I use him here as a scale reference. So basically, you have two field plates. One of the field plates you can see here. The other field plate is hidden from view. It's on the other side of this cylindrical structure, which is placed in this box. And this cylinder can actually rotate. So in this configuration, the field plate that is not in view is actually in the light path of the telescope, and you can observe it. So the photons will come in there, hit the mirror, which is behind this protective cap, and will then be focused onto the field plate. And the other field plate that we can see right now is in a configuration where we can actually place fibers onto this. So this makes this instrument very efficient because you can observe with this field while configuring fibers on the other. And how does this configuring work? Well, they're using robots, in this case, two Cartesian assembly robots that very accurately place those fibers onto the field plate, which is then swung into the light path of the telescope. Good, a little bit more about this field plate. So we're now in the technical section, you might have noticed. So we have the two field plates, A and B, and each of these field plates has roughly 1,000 fibers. And every fiber subtends 1.3 arc seconds on the sky. Also, each of the field plates actually has 8 guide fibers, and these will become very important for the observing mode I will introduce to you very shortly. But before I do this, we really need to talk about timescales. This is due to the fact that configuring a field of roughly 1,000 fibers takes roughly 55 minutes. So this 55 minutes basically gives us a window of observation. So you configure on one field and you observe on the other. So you have roughly an hour of observations while the other field is configured. But in addition to this, actually, every time we switch the field plates, we need to do calibration exposures. And at the moment, they're on the order of roughly 20 minutes. This will go down in the future, but at the moment, this is what we have to work with. And also for each exposure you take, you have a readout time of the CCD of roughly 3 minutes. So you take 3 exposures, you have 9 minutes of readout time. So these two factors down here produce relatively large overheads in terms of timescale. So what one actually wants to do is you want to place, of course, as many targets as possible onto these fields to allow for efficient observations. But let's say you want to look at bright stars. Well, bright stars do have not a very large number density per area compared to fainter targets. And you can see this here easily, where we plot stellar magnitude versus mean number of stars per square degree. And if we go to 10 stellar magnitudes, we only have 10 stars per square degree on average, which means for WEAF, this would be 30 stars. And you don't really want to get a massive observational overheads for 30 stars with WEAF. So we actually need to find a way around this. And also, but now you can actually say, why would you want to look at bright stars? They're not that interesting. Well, if you're interested in exoplanet hosts, then they are extremely interesting. And this is due to the fact that we get the best characterization in terms of stellar as well as planetary parameters for these bright stars. And also what's very important is in studies comparable to WEAF, like Apogee, for example, these are underrepresented in these surveys. And this is due to the fact to this observational efficiencies. And you can see this actually. So here on the right, we plotted the fraction of the total known host star data set that group per magnitude pin that has actually apogee coverage. And you can see if you go below 11 magnitudes, it goes down quite a bit. So as I said, this is due to these inefficiencies introduced by these low number density fields. So this is double unfortunate because Plato in 2026, the next exoplanet discovery mission, actually places its highest priorities on targets below 11 magnitudes, and it is estimated to find roughly 10,000 new planets around those. So I'm convinced that there's definitely a need for an efficient characterization of all of these upcoming future exoplanet hosts in terms of stellar parameters and abundances. And one way to do this is the new observing mode on WEAF that I will now present to you. It all comes down on how you define your field. So if you look at the circular WEAF field, we have 3 fields here. And if we define them in respect to a central guide star in each of the fields, we are able to superimpose them. And after this superposition, we can actually place the fibers onto these superimposed field configurations. And for observations, what this means is you basically hop from one central guide star to the next on the sky, and at each offset, you illuminate a different set of fibers. So making this very efficient, you only have to do one calibration cycle, and you basically just end up with overheads from the readout times. So to enable this, we actually have to solve the geometric set cover problem, which in mathematics is basically just a problem of covering a set of points with a certain geometrical shape, in our case, a circle. And we want to minimize this number of circles while maximizing the coverage. This is for large sets of points, or in our case, stars, of course, relatively computationally expensive. So for 100 stars is easy, but if you go for, I don't know, 60,000 stars, my laptop would work at least a week if you want to do this very exactly. But there's, of course, we opted for a heuristic solution to enable this more smoothly. And what you can see, what our algorithm basically does is it first places circles around WEAF guide stars. So we overlay the WEAF guide star catalog on whatever catalog we want to look at. And then we just start placing circles. These circles are, of course, need to overlap because you cannot mathematically cover a set of points with circles without overlap. So you need to allow for this flexibility. And then we can just assign stars to the individual fields. And last but not least, we check which of these fields we can actually superimpose. And then we group them in these, what we call field batches that will be observed in the same run. So we run this algorithm on the following data set. It's the WEAF Twilight Survey initial field, so what we start out with. And so the WEAF Twilight Survey is sourced predominantly from the Plato long duration fields. You can see them here plotted as the red points, and then we extend it by Gaia DR3 bright stars, which you can see here plotted as the gray points. Also, the Kepler field of view is this the blue, are these blue little squares, and then you can see known exoplanet hosts and candidate hosts as circles and black diamonds, respectively. The magnitude range of our sample is between 6 and roughly 11.5 visual magnitudes, which is quite high because WEAF is only at the moment made for basically it starts at around 12 magnitudes. So we have mostly F, G, K, and A types in there. And as the name suggests, WEAF Twilight is a twilight survey. So we will enable the pre-characterization of future Plato targets, as well as acting as a pilot for this new observing mode. So basically testing out if this really works under regular survey conditions. And also this will, of course, if it goes well, allow us to look at these low number density fields without sacrificing any observational efficiency. So now you can see how the algorithm is performing. So here you can see the same field in deprojected radix space, so a little bit of a different geometry, but still the same. Only with guide stars, and this is the guide star number density by pi square degree. And you can see there's a relatively stark gradient. This gradient comes from here we have the disk, and in this direction we look away from the disk. If we now also, since we're a twilight survey, all these guide stars are around 14.5 magnitude. We need these relatively bright guide stars due to the twilight conditions, of course. So if we run our algorithm on this, we actually get a coverage of 97%, which is quite good for 10 minutes of computational time. So we are quite content with that. But now you can say, okay, you have all these fields, why not start observing? It's not that easy, unfortunately, because the telescope also needs more guide stars per field to acquire the target and to guide on the target. So we need for each of these fields one center and two off-center guide stars. And if you think about it, if you want to superimpose these three fields, it becomes very apparent that you can use the same guide fiber for each of the central guide stars, but you will never be able to use the same guide fibers for the off-center guide stars. This actually was more complicated than we expected, but we wrote a code for that actually does this. And here on the right, you can see the geometry outlined. So here the black circle is, of course, the weave field of view. These black dots around it are the fiber gates where the guide fibers come out of. And the dashed gray line is the region that the guide fibers can reach. So they can only reach these cones. This is due to the fact that they must never cross in between fields. So our algorithm, basically, this is a merged field configuration of two fields. These are all guide stars. And you can see that our algorithm finds the right guide stars. And for the remaining ones, if it's a two, in this case, only a two field batch, we can just assign one of the remaining fibers to the central one. So we have these fibers allocated. So this, in theory, allows us to allocate fibers for 3 fields per batch. And here we can look at how this behaves with the number of available guide fibers, because like real life always is complicated, not always all of the guide fibers are working. So for 6 guide fibers, we can actually see here the same plot as before, but the green circles now show us which of the fields have perfect guide fiber location. And you can see that this number increases from 6, 7 to 8 guide fibers. You also can see the gradient in the disk again. So it gets a little bit better at 8 guide fibers, but we would expect this to be significantly better if we go to faint the magnitudes again. We're also only looking at 14.5 magnitude stars, guide stars, which means there are not as many of them. So unfortunately, at the moment, we have to work in this scenario. We only have 6 guide fibers, but these are 1,200 fields that can be superimposed and looked at. And this is, of course, a much too large of a number to be actually be realistically looked at an weave open time survey. So we had to do a subselection, and this subselection basically focuses on known exoplanet host stars in fields. So we only select fields that have known exoplanet host stars, plus they have a perfect guide fiber coverage. And then we designed 2 priority classes. For the phase 1 of Weave Twilight, we decided that we want that the first priority is placed on fields that have already apogee coverage. And this is due to the fact that Weave is in the beginning and we want as much comparison data as possible. But for phase 2, we will then go to other fields that do not have any spectral coverage or not much spectral coverage. So actually, I'm proud to say that we were awarded 37.8 hours for this proposal. And we have this accounts to roughly 200 observations. So we will be able to look at most of the northern portion of the Plato Lobs field in our subselection, of course, not the whole. But one of the goals would be at some point look at the whole Plato Lob field. Okay, so now talk a little bit about target yield. We expect to get roughly 6,000 bright stars. And if you look closely, you can see for field plate A and field plate B, we have slightly different target yields. And this is due to the fact that at the moment, the broken guide fibers on each of the plates are not in the same position, introducing other geometrical effects. So not all fields that have a perfect guide fiber location on field plate B do so on field plate A, and vice versa. Also, we actually are able to have access with the Wilhelmshaven telescope to a very small portion of the southern Plato long duration field. And this will give us additionally 800 targets, bringing up the number to roughly 6,000 bright stars with 68 confirmed exoplanet hosts. So for phase 1, I think this is quite good. And let's keep the fingers crossed that the phase 2 will actually exist. And we actually were able to implement this observing mode over the summer. And we had very recent test observations by the end of February, looking at a few of these actually southern fields with Weave. And I can show you now the spectra from Weave. Please don't share because they're very preliminary. Please don't take photos. It's just preliminary results from the L1 pipeline in this case. So this basically means that they are just stacked spectra. Tellurics are removed and also sky subtraction has been done. This is a relatively bright star of 6 Gaia Gmax, and the total exposure time was roughly 300 seconds, not roughly, exactly 300 seconds. We find that the mean signal to noise per pixel is pretty good in the green as well as in the red arm, which is not surprising for a 6 Gaia Gmax object. But it actually showed us that the pipelines can handle bright targets very nicely. Also, for a little fainter source at 9 magnitudes, still faint in my regime, basically. But we also have good signal to noise, 75 mean signal to noise per pixel in the green, and a little bit more, 145 in the red. If we go to fainter targets at around 11 magnitudes, we still end up with a mean signal to noise of roughly 20 to 25. So this is quite nice. And what we also did is we actually took some of the data and were curious and just put it into the L2 pipelines, which are actually deriving stellar parameters as well as abundances, if all goes well with David and me. But so we're working on the abundances right now. So what you can see here is a zoomed in version of the red arm of one of the targets. And what the L2 pipeline does, basically, it uses a chi-square minimization approach, comparing models to observational data. And you can see here the best fit model plotted in red versus the data plotted as these black points, basically, little circles. And you can also see insets of different spectral, different absorption lines that are important for chemical abundance derivations. And you can see that the models are pretty spot on, which is nice, and which is also a very promising sign for the future of Weave, actually, which I'm very glad that this turned out this way. So I can now basically give you a little future outlook of what you can expect from Weave Twilight. Well, first of all, this survey will actually enable us to harness the synergies between Plato, Gaia, and Weave very nicely in terms of calculating very precise chemodynamics and also efficiently characterizing the upcoming Plato or a part of the upcoming Plato targets. Also, if all goes well, this will leave us with a homogeneously derived stellar abundance dataset in which we can actually search for these planet-star connections I have told you in the beginning of this talk. So if all goes well, our first science data is expected to come in May 2025. Fingers crossed, I'm not quite sure if this is going to hold, but still I'm optimistic. And in the best case scenario, November 2025, we will finish the phase 1 observations of Weave Twilight. Then we will, of course, reapply for more time, or maybe even be able to work together with other survey groups. We will see how this is going. After this, if this is really successful, then we will actually make this mode accessible to the public. So in the future, if you want to use a low density field mode on Weave, you will actually be able to select it for your proposal. And yeah, this is basically our plan. So let's hope that this works. With this, I actually just put up my summary slide and want to thank you all very much for your attention, and I'm looking forward to questions. Thank you.
Thank you so much, Thomas. Questions? Jerry?
Very good work. Thank you for your presentation. Any plans to extend the survey from the AFGK star to like M stars? There won't be so many bright M dwarfs there. No?
Exactly. The thing is, extending the survey just as an input catalog, yes, but with the observational mode, there will probably be no need because the Weave GA survey will look at a lot of the M stars as well. And so So, but yes, I would like to actually extend this to a nighttime survey as well. But currently there are no fixed plans in this direction, but we would love to do this. Yeah.
Thanks very much. Very interesting. You mentioned the synergies between Plato and the Gaia, as well as we. Just wondering what you think the Psyche mission might also be able to contribute. So not directly related to what you've been presenting today, but I was wondering if the kind of very dense asteroids or asteroid size objects that Psyche will be looking at, which is formerly a core of a planet, will you be able to use that data when it's available to work back, looking at the core of a planet, in situ measurements of that, then work from that to determine what kind of planet it was, what kind of star it came from, and perhaps the accretion disk that formed it?
I mean, I'm pretty sure that there will be this will be a viable way, because if you look at the Psyche mission, if you look at this planetary core it will be visiting, I mean, this will give us enormous insight in terms of if it's from the solar system, if it has some relation to the molar ratios with the solar abundances, for example, then this will either, I mean, yeah, of course, there are large areas we can actually work with. I think the more data we get from our solar system, the more it makes us able to understand our solar system. But it's not actually, if it's not, we don't really know if this is completely true in other systems. But let's assume it is. Then I would say the Psyche mission will definitely expand this types of research and will bring us more insights. I think I have not really thought too much about the Psyche mission, to be fair, but I think it's definitely a good potential for further studies.
Thank you.
More questions?
Thanks a lot for the very interesting talk. I'm involved in Plato for the astroseismology studies. So one question I had was, how many targets do you realistically expect to observe in the Plato field? Mostly in the north, or is it all of them? Or?
It's nearly all of them. It's nearly all of them. So, I mean, of course, every time you work with something like Weave, where you define these fields, sometimes some of the fibers will not really end up on the star or will not be able to be deployed because there's another fiber in the way, for example. So you will have losses in this regard, but you can place priorities. So what we did is we placed at the moment priorities for fibers to be definitely placed on exoplanet hosts, and nearly all of the data. I can show you again the initial fields. So the initial fields basically have the whole northern Plato set plus these extended bright stars. And if we look at our final fields, this is basically, I mean, I think this field is not in the Plato field. All the others are in the Plato field as well as in the Kepler field. But again, you have to think about, there's a magnitude cut. So we are between 6 and 11.5 visual magnitudes. So all the M dwarfs in the Plato field will never be observed, of course.
Well, I'm mostly interested in the G and K, so.
Okay, then you're in luck.
Questions? There's time for a couple of more questions. Maybe I can ask. As you said, we are always asking for more data. Do you think that something similar will be possible with Formos in the southern hemisphere?
Yes, I mean, it would be definitely technically a different challenge because, I mean, the fibers are kind of fixed. They only rotate, I think. But yes, it would, in theory, I think, be possible. We actually, so my supervisor and I, we actually talked about the foremost example for something we might do in the future, but it depends. I think there are already surveys that's starting to work on the Plato fields with foremost. So I'm not quite sure how we continue this, but this technique in theory, yes, it could work with foremost as well.
Thanks. Last question. Don't be shy, students. Of course. Someone also in Zoom could just write or speak loud if any questions in the Zoom.
have a very naive question. In a planet like the Earth, how do you calculate the magnesium over silicon?
Yeah, this is actually this is a good point. This is a good point. So how they do this for exoplanets, for example. So for the Earth, what we can do is we can take basically measurements. We can look at the asteroid belt. We can look at the Earth directly. But for exoplanets, it's more difficult because for the most targets we actually have somewhat relatively realistic ratios of these elements. For example, they come from the stellar abundances in the beginning. So there's basically, so they use the stellar abundances if there are no direct measurements to basically infer over a very complicated process, which I'm definitely not qualified to talk about in more detail, to actually get to the planetary masses. So it's a relatively complex field, and of course there are many biases. So most of those are of course estimates in this case. So,
but for example, in the case of the Earth, to do that, I mean, to analyze the Earth directly, you would need to assume homogeneity.
Yeah, sure, but I think in the Earth example, if you go to planetary crust material that has not been really changed over the years, so there are some places where you find very old material, and you look at the ratios, and also you look at the ratios, for example, in the asteroid belt from meteoroids that fell to Earth, you can actually get a using various techniques get a estimate of the magnesium silicon ratio in Earth, for example. So this is a geology. This is actually a geology question, but still, yeah. And you can then, of course, compare it with the solar abundances, and then we see for Earth, Mars, and the Sun that they are within 10%, which is quite remarkable, I think.
Anyone else? Okay, in that case, let's thank speaker again. And if you are interested in joining us tomorrow for lunch, just let me know, okay? Thank you so much.
It's always a bit daunting, I must say. I hope we will serve you. Yeah. Glad that's over.